So we'll finish up inverses here today, and then start talking about transformations, I think. So yesterday, we've been talking about finding the inverse of a function when it's represented as an equation. And I want to do a few more examples of this, where it's we see some more complicated examples. So let's say we have the function y equals 3x squared minus 4. If I want to find the inverse for this, what is the general procedure I do? I solve for x and swap the x's and y's, right? Okay, so what should I do first? Add 4 over to both sides. Then what? Divide by 3, very good. And then what? Square root of both sides. When I do that, what do I have to be wary of? Plus or minus, yeah. Oops. Yep, sorry. That's an oops. Absolutely an oops. Yeah, Goober did good. And then the last step would be to swap. And then what do we observe here? What can I say about this guy? Well, yeah, that is true. We can say that. It is the inverse. What can we? Yeah, so Anne says this is not a function. Why? What about this is telling you that, Anne? Yeah, because of the plus or minus. Yeah. Now, stop talking, please. So that seems kind of lousy that if we have a quadratic like this, that we can't create an inverse function for it. And the similar thing kind of happens when we start talking about these trigonometric functions. But there's a trick we can pull, stop talking please, to address this situation. And what we do is we restrict the domain. So let's say that we are finding this function, but we've restricted the domain to only talking about non-negative x's. So when you're given some other piece of information about the x's, we call that a restricted domain. Nothing changes in the way we do this until we get to this step. If I know that the x's have to be greater than or equal to 0, that allows me to drop the minus from the plus or minus, because I know that x's have to be non-zero. Everybody okay with that? Or I'm sorry, have to be greater than or equal to 0, not non-zero. Everybody's fine with that? This is the situation why I like to do the swapping of x and y's last. Remember we talked about the other day that it usually doesn't really matter when you do that. But the restricted domain doesn't make a lot of sense in how to use it to get rid of the plus or minus if you swap the x's and y's in the beginning. You know what I mean? So this is the reason why I like to do that as the second step. So if I make a function now, I get a function, right? What's the only downside of this function? Well, it's only going to solve for x's that are greater than or equal to 0, right? Like if I'm trying to if I say y equals 10, and I want to find the x that goes along with it, and I use the inverse to do that, it's only going to give me the positive x and not the corresponding negative result. Is everybody okay with that idea? Raul? So it'll tell you in the beginning. Like this would be the original, would be the given 2 problem. So you'd have that inequality, you'd see it right from the get-go. I don't think this happens in the homework, but we're going to do this later in the course when we build trigonometric inverses and kind of show you what those are doing and how those work and why we have to be a little bit careful about the answer we're getting from our calculator, because it's often not exactly the answer we're looking for. And this is a nice kind of lead into that I'll refer back to. Is everybody okay with this idea, though? Let's do another one. So what if we want to find the inverse for f of x equals the square root of 12x plus 5. So let's start by replacing the f of x with a y. And then we're going to solve for x. The first step we should do is square both sides. And then we'll do what? Subtract 5. And then divide by 12. And then we'll swap our x's and y's. Does anybody see an issue here? Anybody see an issue here? What if I compute f inverse of negative 1? Everybody's okay? So no issue there, right? Seemingly. So it tells me that the point negative 1 comma 1/3 is a member of f inverse. Right? That's what that means? Yeah. What would that tell us about f then? Right? Negative 1/3 and comma negative 1 should be a member of f. Does that make sense? Can I get a negative value as a y-coordinate from this? No, right? So there's a little bit of a domain restriction going on here as well that we have to be a little bit careful of. So while we don't care so much about this issue right now, it will become an issue later on when we look at inverses of trigonometric functions in more detail. But I just want to point out some of these little things that we got to be, well, not careful about now, but we have to be mindful about kind of going forward. Sam?
What is the restriction?
So here is the issue, is when I take and I square both sides, really you're getting the absolute value of 12x plus 5, remember that if I take the square root of x squared is the absolute value of x. Now usually we omit the absolute value for simplicity's sake, but here where the domains and ranges aren't exactly the same, there's a little bit of an issue there, and this problem is a lot more complicated than it at first glance once we have that absolute value in there.
So what this is like for x has to be greater than or equal to 0?
Yeah, basically that's kind of what we're saying. Well, when you take the square root of something squared, you're guaranteed to get a positive result, right? So the square root of something squared, or the something squared square rooted, is kind of the definition of an absolute value. So yeah, we really have this extra contingency here that the inverse works provided that the x's that you're putting in are greater than 0, or greater than or equal to 0. So it's still a function, it just wasn't working quite the way we expected it to as an inverse, right? It was, without that restriction, it was giving us points that weren't actually members of f. It gave us everything that was in f, but it was giving us some extra stuff that wasn't. Does that kind of see that? Again, these details that we're talking about right now are not something I'd expect, like, if I was testing on this, would not be something I'd expect you to talk about in a test setting, or to notice these little, like, oopsie daisies, like the domains don't really match, and this is maybe not exactly what we mean as the inverse, or working exactly as an inverse. But they're things I want us to kind of get used to thinking about going forward, because it becomes pretty relevant later on this semester. Okay with that idea? And again, if gets to test review time and you want to ask more clarification about, like, what is kind of fair game and not fair game, I'm happy to answer those questions later on. Okay? Again, like right now, I'm happy to get to this without any of the extra discussion about, like, ooh, this doesn't quite work right. Maybe it needs a little bit more going on there. But for right now, we're not interested in that. If you can at least just notice when I point it out to you that there's something jiggity going on, I'm good with that. Okay, so again, we'll start by replacing the function notation with a y equals notation. First step I should do is dividing by a fraction is the same as multiplying by its reciprocal. So let's just multiply by -2. It's the same thing, but boy, that's a heck of a lot neater than dividing by the negative or by the fraction. Everybody agree with that? Okay. Okay. Now what's up? Yeah, so we want to take the log of both sides. Which log? Log base 3 would be the easiest one. You want it to match the base on the exponent. You can do log of any base, but there's like a little bit more extra crapola you have to deal with at the end that you don't have to if you just do log of the matching base. So let's do that instead and not have to deal with some extra crapola. Everybody happy there? Okay. And then I should do what? Divide by 4. I'm going to write it as 1/4 out front. When it actually comes time to deal with the log, it makes life a little bit easier not to have the log in a fraction. And if you don't remember all the details of how to deal with logs, that's okay. We end up reviewing that a lot in second semester anyways. The fact that you knew to use a log here was a great sign, and that some of us knew which log to use, an even better one. And then our last step would be to swap our x's and y's. What did I call this? I think I called it G, right?
Yeah.
Does this look okay to everyone here? Are there any little domain issues like we noticed in the previous two? It turns out there's not. You might at first glance think that maybe something's up, because if you remember back from last year, can we take the logarithm of a negative? No. But all that's really telling us then is that these x's are just going to be like less than 0, which is fine. Like you can have negative values for x because it'll give us a positive value inside the logarithm. And then the problem is really solved. We can't take log of negative 2, but we can do log of negative 2x is no problem. Is that okay? Just as a review there's no domain issues with this one, though. This actually works just as we'd expect. And our last example, oh, and by the way, there's like a bunch of simplifying you could do to this expression of logs. I don't need you to do any of that right now, so. This would be fine. It's non-standard. Like the standard way to write that is like putting the fraction in front. Because it's likely we'd want to use the power property at some point and move that into the exponent, which is more natural when it's written as a coefficient than as a fraction. It's not wrong to write it that way, but it just, if you're looking at answers on like a multiple choice test or whatever, I doubt that they would represent the answer that way. And rather, they'd probably represent the answer this way. Yeah, I mean, it's like, you know, like writing this versus, you know, this. You know, like it's the same thing. It's just like how you want to write the fraction or whatever. Or 7 times 1/3 instead of 7/3. It's still the same thing. It just, conventionally, you're more likely to see this typed in than you would the other one. They're both correct. I would mark one wrong and the other not. Okay. This, I think, is the last one, was my plan here, looking at my notes. Yeah. All right. First step. Write it as y equals notation. Then what do you want to do? Good. Multiply both sides by 3/5. Everybody happy there? What does this ln symbol mean again? Natural log. And what is that? What does natural log really mean? Yeah, ln of x is log base e of x. Yup, good. You guys must have had a good Algebra 3-4 teacher or something.
Mr. Cork, I do it.
Okay. So to cancel out the natural log, what do we need to do? Well, you're not going to use a log. Yeah, you're going to use the exponent base e. The way I like to say this is I like to say big E. And when I write it down on my sheet of paper, I tend to write an absurdly big exponent base just to remind myself I'm not multiplying both sides by e. I'm putting e as the base of both sides. So it is a big E. And then to finish this off, we'll add 1 to both sides and divide by 7, right? All right. Everybody okay with this one? Okay. Stop talking, please. Questions about finding these inverses from an equation kind of situations? I think we covered all the situations that I believe that you are equipped to handle at this point. Sam?
You know how to do this? You need to know how to do this log one, this situation.
Mm-hmm. Yeah, you'll see it in the homework. Okay. So in terms of concepts from Algebra 3-4 that are particularly useful to us in first semester, this is one of the most important concepts, the graphical transformation. So when we talk about transformations, this is something that hopefully you recognized from your geometry course. I know that was a long time ago. There were 4 types of transformations you talked about in geometry. So translation, which is the up, down, left, and right, that I heard somebody say. And that's, when we say reflection, really we're talking about across the x or y axis. And the third kind is dilation. That's like a stretching or shrinking. Rotation was the 4th. We're not going to worry about rotation in this course. Or really any of, stop talking please, in any of your high school algebra courses. That's kind of a linear algebra topic if you're going to talk about a rotation of something. Or a graphical transformation involving a rotation that's not a 90-degree rotation, would be like a linear algebra topic, which is way beyond the scope of this course. But potentially, if you're doing if you're an engineering college student, you might see that later at some point. Okay. So if we talk about so these are transformations we talked about in geometry. We're going to apply these idea of a geometric transformation to an algebraic setting, namely to a function. In geometry, you did translations and reflections and dilations to things like a square or a triangle, right? A square or triangle in the xy plane, though, is just a set of ordered pairs, right? On any of those segments, you have infinitely many points, and they're just sets of ordered pairs. This sounds a lot like a function, which is also just a set of ordered pairs with a little specification on how many times you can use that x coordinate. So anything you can do on one set of ordered pairs, we can do for the other. We can do these same transformations to a function. So one way that we use, especially in trigonometry, to graph functions is we understand the parent function and the key characteristics of the parent function, and then we view every other graph as some kind of transformation of that parent function. So when we say the parent function, what we really mean is like the simplest version of a given function type. So for linear functions, our parent function is y equals x. For quadratics, our parent function is y equals x squared. For square root functions, our parent function would be y equals the square root of x. You get what I mean by simplest version of that type of function? Square root. Yes. Yes. So what we're going to say here is for any parent function, y equals f of x, any member of that family of functions, stop talking please, can be written in the form y equals a times f of c, 1 over c times x minus h plus k, where, and then I'm going to give some specifications for what each of these coefficients do. So for what the a, c, h, and k do in terms of transforming that parent function. So when I look at this, let me actually write out the rules. That'll be easier first. So again, what we're doing here is I'm listing the criteria that describe how these coefficients are changing the parent function. So if that C coefficient is negative, it's going to cause a reflection across the y-axis. If it's positive, no reflection happens. Okay? If the absolute value of C is not equal to 1, then one of two things can happen. If the absolute value of C is greater than 1, we get a horizontal stretch by that factor. And if the absolute value of C is less than 1, we get a horizontal shrink by that factor. So how can you have a number that's less than the absolute value of 1? It'd be like a half or a third or a sixth.
No, because like if it just says 6, that's 1 over C. So like C would be less than
If the number was 1/6, the coefficient was 1/6, C would be 6, and you'd cause a horizontal stretch.
If 1 over C equals 6, then C itself is what does that
If 1 over C is equal to 6, C is 1/6.
right?
Okay.
Which is less than 1.
Yes.
So even if it appears like it's greater than 1.
Okay. So we'll get to that when we look at some numeric example. But yes, I see what you're saying now. That is correct, and that's the fine way of thinking about it. This would be an expectation that you have these things memorized, yes. But don't worry a whole lot about that quite yet, because we're going to do some activities to help you remember what these things do. And I'm going to go back and point out to you a way of helping remember. Oops. Yeah, you did.
Wow.
Yeah. Yeah. We have talked about this over and over and over again in Algebra 3-4. We did.
No.
Okay. I thought I got it down. I wrote these all correctly. What's your question there? You're good? Okay. There's only 6. So 1 and 3 are reflections, 2 and 4 are dilations, and 5 and 6 are translations. When we talk about the kind of transformations happening. Raul? Yes, of course. Correct. Yep. So we talked about the 3 types of transformations just a moment ago. That's what's going on here. So if I have a point and I'm reflecting it across the y-axis, what coordinate is changing, x or y? X coordinate, right? If I reflect it across the y-axis. If I stretch something horizontally, what coordinate is changing, x or y? X. Okay. If I reflect something over the x-axis, which coordinate is changing, x or y? Y. If I stretch something or shrink something vertically, what coordinate is changing, x or y? Y. If I shift something left or right, what coordinate is changing, x or y? X. Left and right? X. And up and down? Y. Everybody okay with that? Okay. So if I go back and I look at, is anyone still copying? Okay. I'll wait for a minute. We're going to go back and look at that function that I wrote up there just a moment ago and point out something to help us remember.
With Gabe, it sounds great.
I don't know what the Iron Dragon is.
Some would consider it one of the smallest rides. To see your point, but past your heights.
All right. Let's rein it back in, folks. Let's rein it back in. Stop talking. So I'm going to go back and look at this general form here. So let's look at h. What variable is h attached to, x or y? X, right? And notice when we talked about the y's, or the h's, excuse me, we're talking about, we said it was a translation in the x direction. What variable is the c interacting with? X, right? And when we talked about c's, notice that we're talking about the x's. Everybody agree with that? Okay? When I look at the k, which variable is the k interacting with? The y, right? Or the f, which is the same. We know f of x and y are used interchangeably. The k is being added to the f of x. Everybody can see that? So notice down here, the k's affected the y. What is the a attached to? The y, or the f. And when we look over here, what does the a do? It affects the y. Everybody okay with that idea? So that helps a little bit in remembering like which ones do which, because I know that x is left and right stuff or horizontal stuff. Y's are up and down stuff or vertical stuff, right? So that's a little bit of help. When we go back and we think about these guys, if I think about a translation, the xy from this triangle change to the xy in this triangle. I've gone right something and up something, right? So we would have added something to each of the two coordinates, correct? To do a translation. Notice in our function down here, the operation going on between the h's and the k's that are controlling the translations is addition and subtraction, right? So hopefully it's easy to remember that the addition and subtraction ones are the translations. If I think about the reflection, if we reflect across the y-axis, which coordinate changed? The x. And what happened to that coordinate? It was negated, right? So if this was like negative 5, oops, sorry, that would become positive 5, right? If we reflected it. So, which one of these deals with positive and negative? The reflections. Yes. Of course. You're welcome. Usually is not a good question. There's 8 in this one, though. So this is the last section. I don't, probably not the next class period, but the period after that.
Oh, wow.
Yeah.
Yeah.
I'm not really sure when we meet, what days this class meets. I'm only ever like at most a day ahead of schedule. With this new rotational, it's hard for me to figure it out. I don't, but I don't really get a choice now of like moving it around so easily. Excuse me, guys. And then if we talk about a dilation, something happens like this. Yeah, those coordinates got multiplied. And which ones do the multiplication if I look here? C and A. So which ones need to worry about being smaller or greater than 1? C and A. Because when we multiply by a number bigger than 1, things get bigger. When we multiply by a number between 0 and 1, they get smaller, right? Does that help a little bit in remembering what these things do? All right, so let's look at a specific example here. All right, so if I were to try to describe the transformation occurring here, first thing I'd want to do is identify the values for A, C, H, and K. Okay, so A is 2, C is 1, H is -1,
Oh my God.
and K is
4. Wow.
okay. So
Innovation.
I'm going to then list my 1, 2, 3, 4, 5, 6. Notice since the 1 and 2 are both regarding C, if C is positive, there's no reflection across the X, so I'm just going to put a mark there to say nothing happens. If C is equal to 1, there's no horizontal dilation, so I'll just put a slash there. For 3, if A is positive, nothing happens, so I'll put a slash there. If A is greater, or if the absolute value of A is greater than 1, I have a vertical stretch by a factor of 2. For 5, this is about the horizontal lefts and rights. So if H is -1, means we're going left 1 unit. And if K is 4, means we're going up 4 units. So this is the sort of thing I would expect that you're able to do. I mean, you can just put a little slash there, as far as I'm concerned. You just say, like, that's the same thing as nothing happens. You could write out, like, no reflection across the x-axis.
Right, you want to indicate that something happening, that we can't just write it before.
You could leave it blank, but I'd like you to at least, like, have it, yeah. I'll probably have that in the format, like, as your answer. Put like 1, 2, 3, 4, 5, 6. Let's do another. Let's say my function is g of x. So let's say our function is g of x equals -3 times the square root of 2x minus 4 minus 2, where the square root of x is our parent function. So again, what I'm going to try to do is to describe the transformation in words. This is a little bit tricky here, though, right? There's a couple of things to worry about. Yeah, so the first thing I'd want to do is to get this in the form. So remember, our general form that we want is a times, in this case, 1 over c, or square root 1 over c x minus h plus k, right? That's what we're trying to get this to look like, so it'll be easy to identify the A, C, H, and K. So if we do that, we would need to factor out a 2. Everybody's okay there? But I want to rewrite 2 as a fraction with a numerator of 1. So this is what Sam was talking about earlier when he was confusing the bejiggity out of everybody going 1,000,000 miles an hour. Well, what is 1 divided by 1/2? 2, right? That's the trick for how I go and rewrite 2 in the form of 1 over C. So what Sam is basically saying is C is the reciprocal of whatever that coefficient is. So if your coefficient was 1/2, C is 2. If your coefficient is 2, C is 1/2. That's what Sam was trying to explain earlier, but because we hadn't really seen that before, everyone was lost. So if I take 1 and divide it by 1/2, that's the same thing as 1 times 2 over 1, which is just 2. That's the trick for rewriting a integer in that 1 over C form. So it was a little tricky, yeah. All right. 1, 2, 3, 4, 5, 6. What happens in 1? Nothing. Good. In 2. Okay. What happens in 3? Okay. In 4? Good. Uh, 5? And then for 6? Does everybody feel okay doing this? Okay. We're going to stop here. We'll finish up this section next time. We will also